I am Simon Levin from Princeton University, and it's my great pleasure today to introduce Wilfred Ndifon and Lavanya Singh, who are going to make today's presentation. I had the great honor of being Wilfred's thesis advisor. He originally came from Cameroon to Morgan State University in Baltimore, and then I think Towson for some period, and then was a graduate student with me at Princeton before going off to the Weizmann Institute to work with Ruth Arnon, who was working on universal flu vaccine. He's done a lot of work on T-cell repertoires, especially on also on antibody interference and its implications for vaccine design. Great and original work. He became an Einstein Fellow and then the Joint Development Chair for various centers in Africa, and now the Director of Research for the AIMS Global Network. And Lavanya is a virologist at KwaZulu-Natal, molecular epidemiologist, and postdoctoral fellow, and I'll let Wilfred say more about her introduction. Today, they are going to introduce us to an extremely important problem related to pooled testing and using Hypercube designs. And I won't take any more of their time, but turn things over first to Wilfred, who will then introduce Lavanya. So it's a great honor and thrilled to have you here today, both of you. Wilfred, it's all yours.
Thanks a lot. It's really a pleasure. I mean, thanks, Mada, for the invitation. Simon has been my inspiration and mentor for so many years. So it's a pleasure to be able to speak here. So this work, there is a theoretical part, and then there's also an experimental part. I asked my colleague Lavanya Singh, who is a virologist, as Simon has mentioned, and a postdoctoral fellow in the lab of Tulio de Oliveira. She's been leading the experiments aimed at further validating the method, automating it, and also some field experiments, field trials that have been done in South Africa. So really exciting work that she's been doing. I'm looking forward to her part of the talk. But before that, I will give you some details about the method so you understand how it works. But before moving to the details, I want to just give some, provide some context. So for decades, American leadership has been so effective at helping the world to avert catastrophes by dousing fires here and there, that at the start of the COVID-19 pandemic, I think very few people could have imagined the chaos that would come to characterize the response. Globally, we are still a long way from winning the fight against the pandemic. Each country must win for every country to win. Many variants have emerged. Some have really dire consequences for the efficacy of vaccines. And testing capacity remains low. There are some countries where testing is, the effort to test is too little. I mean, it's not enough to give a good picture of what's happening in those countries. And we need to test to know which variants might be coming up, those testing and sequencing to know which variants might be coming up and what we should prepare for in future vaccination efforts. So we need to deploy all the tools available to fight the pandemic. Otherwise, for many years, we'll be dealing with a current situation where we have waves of infection that very deadly, that are causing a lot of destruction around the globe. In the absence of global leadership from the US, other countries have stepped up, and these have typically been small countries with strong and effective leadership. I'm going to talk briefly about one of those countries which I'm proud of, and that is Rwanda. Rwanda is in East Africa. You can look, you see on the map, it's this little dot. The cumulative number of cases in the country is relatively low, and the number of deaths also is not that high. In fact, the effectiveness of the methods that were deployed to control the pandemic have been recognized by a number of institutions, including the World Bank. It's actually one of few countries that in June of last year were considered safe for people to travel to and from by the European Union. And recently it was ranked by the Lowy Institute in Australia as having the 6th best response to COVID-19. I'll say just a bit, talk a bit about the ranking. It's based on variables like number of reported cases and deaths, tests conducted per capita, the positive fraction of those tests. And they looked at these different variables and then ranked countries and then normalized the ranking. So they got a score between 0 and 100. And I've shown here, compare the scores for Rwanda. And so the ranking started from when each country confirmed its 100th case and went on for 36 weeks thereafter. You can see here Rwanda, Kenya, which is a neighboring country to Rwanda, New Zealand, which actually was considered to have the best response, and then the United States and the United Kingdom. Of course, these are not perfect responses. They are just indicative. They tell us that something is being done well here and maybe not so well in other places. Now, much of this, the success the country has had has been due to testing, because you can't control effectively what you can't measure or what you don't know exists. And you need to test to know the scale of the pandemic within your country. And you need to test to assess how well the measures you've put in place to control the pandemic are working. And so the country embraced science as a major source of information of solutions to the pandemic very early. And at AIMS, we were contacted even before the first case was confirmed to help with mathematical modeling. And so, so far about 800,000 tests have been done using pooling, and it has saved the country, based on an estimate made by an economist, more than $35 million. Now, Rwanda is a small country, a resource-constrained country, and also with very low levels of corruption. So $35 million can go a long way towards providing services needed by the population. So let me note also that pool testing, the need to save resources by doing pool testing, is not important only for resource-poor settings. We must all be responsible stewards of the limited natural resources that we have. So we should try to minimize how much of these resources we use whenever possible. And this means using as little as necessary to test and to control diseases like the one we're currently facing. Just a bit of information about some of the people who were pivotal in the introduction of pool testing in Rwanda. Around March of 2020, when we were doing some building models, and the minister who is at the bottom here would use these models in cabinet meetings to inform decisions. I started thinking about the evidence we need for these models, how much data we need, how much it costs to collect this data, and can we improve, can we reduce the costs of collecting the data. So I met Leon Mutesa, who is the national head for testing in the country, a very good human geneticist, and he runs the lab that does most of the testing in the country, and introduced the idea of pooling. And then once he understood the importance of doing this, and this is something that distinguishes Rwanda from other countries. In some African countries, you have to go through a lot of bureaucracy to get this to the main decision makers and have them fund something like this. We wanted to work not just on the theory, but also have this applied in practice and see the effect on the ground. And so to do this, we needed the approval from the government. And so we talked to the minister, who also understood the opportunity, saw the opportunity, and then convinced the cabinet to approve this. So everything moved quite fast, and we were allowed to do and funded to do a field trial of this method in the country. So here is Neil Tirok. I'm able to talk about this, and I think this work was possible because AIMS exists, and Neil is the founder of AIMS, and he was also my theoretical collaborator on this project. So these are three people who played a really pivotal role in ensuring that we brought this innovation to Rwanda. And now it is being used in other countries. It's been exported to the UK, and in fact, is helping with the screening of students at the University of Edinburgh, but also in South Africa. And Lavanya will tell you later about the beautiful work that she's doing there together with Tulio. I won't review the pioneering work on pool testing. I think by now this it's well known. Around March of 2020, when we started working on this, we did not really find, there was no published work on pool testing in COVID-19. And we looked at the theory that had been published at the time and thought there was a more elegant way to do pool testing. So the idea is very simple. So imagine that, so I'm showing here a 3-dimensional cube. It has some length. And now imagine that it would have L to the D cells. So imagine that you have your individual samples in these different cells of the hypercube, okay? We want to identify the infected samples within the hypercube. Now, what we do, here I've shown a hypercube of length 3, again, a 3-dimensional structure. We slice the hypercube. So I have on the different cells, on the each of the 27 cells, a sample. I'm going to create slices of my hypercube. One way to think about this is if you have a plane and you put the plane parallel to one of the faces of the hypercube, and then you move the plane across your hypercube, you move it through your hypercube, you're going to meet these different sections, you're going to create some different sections. So initially you would have a square. So that's the first slice you're going to generate. If you move the plane further, you have another square, and then finally you have the third square. So our slices essentially are D-1 dimensional structures. And these slices, we do the slicing from each of the principal directions of the hypercube. So from each of the 3 principal directions, we construct 3 slices. So together we have 9 slices, and each slice has L to the D-1 cells, which are the samples we studying. And we use our slices as pools. So from this hypercube, I get 9 pools, which I test. Each pool has 9 samples. I pool those samples together, and then I test. Now, suppose I had just one infected individual, one infected sample within my hypercube. Then from each principal direction, only one of the 3 slices will yield a positive test, okay? So essentially from each principal direction, I know what is the coordinate of that positive sample. So I can locate precisely where my positive sample sits in the hypercube. So very, very simple idea. Now this works beautifully when you have only one positive sample. You can have degeneracies, you can have cases where you have more than one positive sample. I'll show you what we do to ensure that you always have, you have one positive sample in your hypercube for the vast majority of cases, and in only a small number of cases would you have 2 or very rarely 3 positive samples. And I would also tell you how we deal with that. So suppose you have 2 positive samples, Now we have three principal directions. It may happen that in 2 out of those 3 principal directions, my 2 positive samples happen to be on the same slice, okay? So then I know exactly what are the coordinates of those 2 positive samples in 2 principal directions. Because no 2 samples can occupy the same cell, in the 3rd direction, I must have 2 different positive slices. And those 2 positive slices will tell me exactly what are the locations of the 2 positive samples. So this is one case which happens in about 10%. If in an optimally designed hypercube experiment, between 10 to 14% of cases, you would find something like this. But it may happen that in more than one direction, I have 2 slices that are positive. Then we have degeneracy. There are many possible combinations of coordinates that are compatible with this outcome, with the test outcomes. So what we do, if we have such a case where there's a degeneracy, we look at one of the principal directions in which we have more than one positive slice. We divide the hypercube into as many parts as there are positive slices in that principal direction. So we have now smaller hypercubes. And then we repeat the same process of slicing the smaller hypercubes and testing. And we have theoretical guarantees telling us what would be in an optimally designed experiment, what is the failure rate once we follow this process, this procedure. So the same degeneracy can happen if you have 3 positive slices. So one simple case is you have in one principal direction, your 3 positive samples happen to fall in different slices. Then you have 3 positive slices in that direction. Now, if in the other 2 directions, you have only 1 positive slice, then you immediately determine what are the coordinates of the 3 positive samples. But if you have more than 1 positive slice in any of the other 2 principal directions, then you aren't able to determine uniquely the positions of the positive samples. Then you proceed, as I described earlier, you separate your hypercube into 3 smaller hypercubes. So these would have d-1 dimensions. And then for each of these smaller d-1 dimensional hypercubes, you do the slicing as before. So one question that one may ask is, what is the optimal dimension? Suppose I have my samples. I want to choose a hypercube to fit my samples in. Do I simply look for any combination of length and dimension that will give me a hypercube that is large enough to accommodate my samples? Or is there a more intelligent way of choosing these parameters? So actually there is, and it's very simple to determine this. If you treat D as a continuous variable, the number of tests you do is L times D. So you can minimize this number of tests with respect to D. And if you do that, you get an optimal value for D, which is the logarithm of N. And from that, you get an optimal value for L, which is actually E. And because L must be an integer, we set L to 3, which is only a small, about 5% larger than E. So our optimal number of tests is LD, where L is 3 and D is log to the base 3 of N. So essentially the number of tests is 3 log to the base 3 of N. And so here at the bottom of the page, you would find a classic result for the optimal number of tests from a method by Dorfman. This is not an optimal method, but it's historically very important. That's why it appears here. We can do the same thing for N and say, what is the optimal size of our groups? So if I have a large population, I may put every member in a hypercube, or alternatively, I may break it up into smaller groups and put the groups in the hypercubes. So we can optimize the sizes of the groups that we try to fit into the hypercubes. And so if you look at So if we have a prevalence of the disease in a population, which we denote by lambda, we can calculate the expected number of tests per person, per individual. And it's just this expression that you find here. And then we can find out at what value of lambda do we have the smallest number of tests per person, per individual. It turns out that we need to choose lambda such that it's equal to 0.35. This is essentially saying that suppose I have a prevalence P in my population. If I'm forming groups, I should form the group such that the average number of positive samples in each group is 0.35. If we do that, then we have designed the test optimally in accordance with the rules that I have just described. Now we can also think about the failure rate. The calculations here are a bit more involved. I will try to provide just the intuition behind this. And anyone who needs more details, I will be happy to have more detailed discussions to explain exactly what we did here. And much of it is just combinatorics. But first, I need to tell you what the assumptions are. To make the calculations easier, we assume that we construct our hypercube and then we randomly place samples in the hypercube. But as we placing these samples randomly, no two samples occupy the same cell. This is an assumption that is valid when D is large, when the number of dimensions is large. Then the probability that two samples occupy the same cell is low. And so we do that, and then we slice our hypercube, and then we do the test. If you do the test, remember we discovered that the optimal length of a hypercube is 3. So if we do the test, then we get these triples. So in each principal direction, we can have either 1 positive slice, 2 positive slices, or 3 positive slices. So these are the outcomes, the possible outcomes we can have in each principal direction. Then we can ask, suppose I have K positive samples in my hypercube, what is the probability that in a given principal direction, I'm going to have any of these outcomes? And then, so if you think, again, this is just, you can think about having 3 boxes, and then you throw K positive samples into those boxes. So if you have 2 positive samples, you throw into 3 boxes, what is the probability that both appear in just 1 box, or that they appear in different boxes? So this is essentially what we are calculating here, but we integrate over all possible values of K conditioned on lambda, which is the expected number of positive samples in our hypercube. So if you do that, you get this expression for the probability of getting the outcome sigma equals 1, and the probability of getting the outcome sigma equals 2, and the probability of getting sigma equals 3. Now we can use this. There are additional formulae which I didn't present here, but their derivation follows a similar simple reasoning. So we use these formulas to calculate the failure rate. So let's look at this equation, for example, and think a bit about what it's saying. So if I do a test, just 1 round of the slicing test, I have sliced my hypercube as I described earlier, and then I have done the test. Now, if I have just a single positive sample in my hypercube, there's no problem. I can uniquely identify it after a single round of slicing the slice test. If I have more than 1 positive sample, then suppose that in all but 1 of my principal directions, I have sigma equals 1. Then I can use the dth direction to determine what are the coordinates of my positive samples. So this question is asking, what is the probability that I'll have a configuration of the slice outcomes in each principal direction, the sigmas, such that I am unable to uniquely detect the location of the positive samples after the first round. And this part is just the binomial distribution. I have a probability P of having sigma equals 1 in a given direction. And I am asking what is the probability that in small d out of capital D directions, I'm going to have sigma equals 1. So this is the binomial probability distribution. Now, to do the calculation for the subsequent rounds, we distinguish between different cases. So for example, to make the calculations simple and transparent, you can think of the case where in the first round of slice test, there's no direction in which sigma equals 3. Or another case where there is exactly one direction in which sigma equals 3, and in another case where there is more than one direction in which sigma equals 3. These two cases actually dominate the possible outcomes in an optimally designed hypercube slicing experiment. And so those are the two cases that I'm going to focus on. But the third case can similarly be analyzed without much difficulty. So I've just put here the frequencies of these different cases that I've mentioned. If I have no principal direction with sigma equals 3, then I know that all my positive samples lie within a smaller hypercube with 2 to the D2 cells. Remember, D2 is the number of principal directions with sigma equals 2, with 2 positive slices. So I divide my hypercube into 2 parts, and then I repeat the slicing test for each of the parts. In the first round of slicing, I had the expected number of positive samples to be lambda 1. So because I'm creating 2 smaller hypercubes in the second round, the expected number of positive samples simply decreases by a factor of 2. And in the jth round, it decreases according to this formula. If one of the principal directions has sigma equals 3, then my positive samples will lie in a hypercuboid, right? So I have only one direction with 3 positive samples. The rest have at most 2 positive samples. So I have a hypercuboid with 3 times 2 to the D sub 2 cells. And I repeat the process I described earlier. I divide my hypercuboid into 3 parts. So I have 3 hypercubes with 2 to the D sub 2 cells. And then I do I repeat my test. I just want to highlight the fact that the expected number of positive samples in the second round, in the hypercubes found in the second round, would be given by this formula. So in the jth round, more generally. Now we know what the failure rate is in the first round. We can also ask what is the failure rate in the second round. So again, this is just, in these brackets, I have essentially what I have here. This is 1 minus the probability that I have sigma equals 1 in all but one principal direction. So I have to look at these probabilities and sum over all possible values of D sub 2. This is the number of principal directions I had in the first round of slice test with sigma equals 2. And it's starting from 3 for the simple reason that if we start with 2 dimensions, so if we start with a square, right? So we have just samples that can go into a square. In the second round, once we separate this square into different parts, whether 2 or 3 parts, we end up with lines. And if we slice those lines, we end up with points. And those are the points we test. And the points are essentially our samples. So there's no chance of failure if we have D equals 2, big capital D equals 2 in the first round of slice test. So the only interesting cases occur when we start with at least a 3-dimensional structure. And so we sum over all of this, we calculate this failure rate, and this is just the probability, the binomial probability for a particular number of directions with sigma equals 2. And in this first case, I've considered the case where in the first round, there is no principal direction with sigma equals 3. And we can do the same calculation in the case where in the first round, we have exactly one principal direction with sigma equals 3. Again, I may have gone too fast, but I hope you have an intuition for how these formulae were derived, and I'm happy to have a detailed discussion with individuals later who are interested in this approach. So just to mention the information theory bound for these kinds of tests that produce just two possible outcomes, either they're positive or they are negative. There's a well-known result giving us the minimum number of tests that we can do to identify all the positive samples. There is a method that is a binary approach to testing. Basically, you start by dividing all your samples into two groups. You test each group. If both are negative, you stop. If one group is positive, you go into that group. You divide again into two, you test, and you continue until you cannot test any further because you have already identified the positive samples. And then you repeat this until you get all the positive samples in your population. And so this test is quite efficient. You need to do about 1.88 times fewer tests than you would need using the Hypercube testing approach that I have just described. But the advantage of our approach is that it is very fast. So with this binary testing approach, you need log to the base 2 of the sample size, number of rounds of testing. Whereas with the Hypercube testing approach, sometimes you need just one round. If everything is negative, you stop. You can do the second round, and we have done calculations showing that with a very high probability, the test can stop in the second round. But with probability less than 0.1%, you can stop in the third round and fail to find the positive samples. So we have quite a low failure rate if we go up to 3 rounds, compared to many more rounds that are required with the binary testing approach. This just gives you an argument saying that you need as few rounds as possible, because if you have an exponentially growing pathogen, the longer it takes to detect infected individuals, the more the disease spreads. So I've talked about how the advantages of this approach over the binary testing approach, which is quite efficient. But what are some of the limitations? These limitations, by the way, are shared by the binary testing approach. And in fact, the last limitation I've listed here is worse in the case of the binary testing approach. But these are important things that as we discuss and work with experimentalists, we're also thinking about ways to help them deal with this. For example, if you construct a 3D hypercube, you have 27 samples, but then you have 108 pipetting steps, as my colleague, my collaborator will tell you. If you do a 4D hypercube, you have 405 pipetting steps. So this is a lot. And this is basically pipetting each sample that you need to construct these different slices. Another limitation, besides the labor intensiveness of the approach, is that our slices are relatively large. They contain L to the D-1 cells. And so if D is large, then this is a large number. And we know as we pull more and more samples, we lose some of the sensitivity of the test. So the probability of false negatives increases as we increase the pool size. For reasonable pool sizes, I think Lavanya will tell you what the sensitivity is. But there are also things that colleagues are doing to try to circumvent this particular limitation. So I'm going to end here, and then I will hand over to Lavanya, who will tell you about some exciting work that's being done in the lab.
Thank you very much, Wilfred. We'll wait to listen to Lavanya's presentation. I just want to make a small point as she pulls the slides up. The person who first came up with the concept of Latin hypercube design, Dick Beckman and his collaborators, is somebody who is in our group, actually. He's retired from Los Alamos, but it's rather interesting. So I've sent an email to him saying that, there's a very nice use of the design he has come up with long time back. And Dave Higdon is here as well, who I'm sure can say more. But I will certainly introduce you to Dick Beckman, who was the one who came up with the idea of LHDs for sparse designs.
Yeah, so actually, that is a different subject. I won't have time to talk about that. It's something else that we also exploring. But I think that this is just from geometry, which is very old, right?
Yeah.
Placing things in a hypercube. What we've done here is just something that's been known from geometry for a very long time. Yeah.
So just to expand a little bit on the principle of the hypercube method, if we consider a 3D hypercube as shown in this image on the left, each vertex or corner represents an individual sample. So the hypercube can then be sub-pooled into 9 slices, which are based on the principal directions of the hypercube. To illustrate this more clearly and to simplify the structure of the hypercube, the corresponding coordinates of each sample is shown in this table here. So based on this pooling pattern, 9 slices can be created by pooling together samples from 9 different individuals. And based on this pooling pattern, if one infected individual is present, then tests on each of the 9 slices can identify their coordinate in that direction. Hence, only 9 tests are needed to uniquely identify them. Obviously, as the viral prevalence decreases, the optimal group size and dimension size can also increase into a 4-dimensional hypercube, for example. To illustrate this in the lab, this is what we do in the lab. Here is an example of one positive sample contained in a 3-dimensional hypercube comprising of 27 samples. So firstly, the swab samples are pooled together to create one individual sample. This is facilitated by the use of an automated liquid handling robot. The sample then undergoes RNA extraction and then qPCR. If the pool of the 27 samples is positive, then 9 slices or sub-pools containing 9 samples are then created. The positive can then be reliably detected in the pool of 27, as well as the respective slice numbers 2, 4, and 8. Similarly, if we consider a 4-dimensional hypercube, which contains just one positive, in this case, it's present in position 2 of the hypercube. If we perform testing of the pool containing 81 samples, as well as corresponding 12 slices containing 27 samples each, then the positive can be reliably detected as it appears in slices number 1, 4, 7, and 11. So these are just some typical results that we've obtained in the lab by doing some 27-fold and 81-fold dilutions, which correspond to 3-dimensional and 4-dimensional hypercubes respectively. The cycle threshold or CT score that we see here, this can be used as a proxy for the viral load. So the higher the CT score, then the lower is the viral load and vice versa. So as we can see, as we increase the dilution, here's the raw value or the undiluted value. This is at a 27-fold dilution and at 81-fold dilution. As we increase the dilution, so too does the CT score increase. It's apparent that we can see some loss of sensitivity for the assay for CT scores which exceed around about 32. But we must note that these typically low viral load samples, they may be deemed as clinically or epidemiologically insignificant since the infection is then not likely to be contagious. So I'll just move on to a little bit about the automation that we developed in our lab. Although this pooling strategy, it offers considerable benefits over the individual testing strategy, it does involve tedious and repetitive pipetting steps, which can be very cumbersome if you have to perform this manually. So for example, if you're doing a 3-dimensional hypercube, there are 108 precise pipetting steps in different combinations. So that's actually the 27 samples plus the 9 pools of 9 samples each. For a 4-dimensional hypercube, this involves a total of 405 pipetting steps, which are the first pool of 81 samples plus 12 pools of 27 samples each. So what we implemented at CRISP is the use of a liquid handling robot known as the OpenTrans 2. It costs about $5,000 and it enabled us to increase human resource time, which could be better allocated for data analysis or experimental setup. It also eliminated the possibility of human error, which, as you can imagine, it can be quite high due to fatigue or distraction, for example. The costs associated with manual labor and the ability to easily replicate or modify protocols based on the starting number of samples and the desired number of pools was also possible by using this robot. So another important feature that we have developed for this workflow is the automatic identification of the positive sample within the respective hypercube. So here we developed a web application which allows you to simply input the number of samples that have been pooled together, and then you can input the number of slices that generated positive results. And the output will be the positives that were contained in the hypercube, and it dictates which positions those were at. Lastly, we implemented the use of a debundling or ungrouping software where we could break down the pooled results into individual sample results. So this was basically a process which was coded in Python and used to apply the qualitative result achieved on the pooled samples individual tests. So it's a very quick and easy solution, and it can be easily integrated to any LIMS system. So it really helps automate this process. In summary, the pooling strategy, together with the downstream automated processes, has led to a significant reduction in cost, kit usage, and turnaround time at our lab. For example, if one assumes a prevalence of 1.2%, which is 1 positive sample in 81 samples, then a 4-dimensional hypercube slicing would consume a total of 13 tests instead of 81. Assuming that a technician will take the same time to do the pooling and individual tests, and a qPCR test costs about $50, testing the 81 samples in 13 tests would decrease the cost to about $8 per test. For lower prevalence settings, where all individuals are negatives, the cost reduction is even greater because 27 or 81 negative results can be achieved by using just one qPCR reaction. So what we have been doing at CRISP is we've been routinely testing a prominent rugby team where the prevalence was relatively low. And during the first 8 weeks of testing these players, all of the samples were tested using pool testing of 27 or 81 samples. It was only around about the 9th week of consecutive testing that we needed to perform additional rounds of slices as the number of infections began to rise. The pooling strategy has proven to be highly efficient. Yeah, so just to stress, this was really, really good for our lab because of the low prevalence and the high turnaround time that we saw. So in conclusion, we were able to describe a new approach to parallel, non-adaptive testing for identifying infected people, which largely cuts down both cost and time. This is preferred to a neo-optimal adaptive testing approach when infection prevalence is still small. We also described the validation in the lab as well as the automation processes together with a field evaluation. Both Wilfred and I would like to acknowledge our collaborators, as well as the CRISP lab and the AIMS COVID-19 response team, and finally the Rwanda COVID-19 Joint Task Force. Thank you.
Thank you very much, Wilfred and Lavanya. This is just absolutely brilliant work. For folks who don't know, this paper has appeared in Nature some time back. We can send you the link. but let Golda then handle the question answer session. But thank you so much. Beautiful work.
Thank you.
Yeah, thank you, Wilfred and Lavanya. Does anybody have any questions? You can unmute or go ahead and put it in the chat and I can read it out.
Maybe I'll start while people are forming the questions. Wilfred, I think this idea that you both have shown, I personally like it because it's very nice mathematics, and then all the lab work you folks have done to show this. And as a computer scientist, binary search method for testing has been the one people had always talked about, and variations. Instead of doing binary, you can do a ternary thing. You can split into groups of size 3 or 4. But I think this has really nice underlying mathematics. You show it works in low prevalence and high prevalence cases too. And also Lavanya showed this value in the lab. One question I have now, and I'm sure others have it, is there's some work going on at our university using water-based samples. And I do not know how one would potentially use your methodology in that case. And also, if we start doing testing for variants, and maybe Lavanya's next, the work she's doing right now, maybe talks to it. But as you get variants, do you have any sense for how you might go ahead and do it, and identify multiple variants at the same time? I quite don't know the exact details, so that's why maybe my question is too naive.
Yeah, thanks. These are very nice questions. So concerning the water-based testing, I will start with that. Lavanya can also jump in regarding variants. In fact, our method is about how do you optimally arrange your samples so that you can more efficiently detect the positive ones. So it doesn't matter what is the source, what type of sample you're using. You can use it with saliva, you can use it, sewage samples. What is more important is the questions you want to answer, right? So we've been doing some work in Rwanda where we are looking at sewage samples, and the question is, if I take a certain number of samples at certain time points from a given location, and I get a certain result, what are the implications for the prevalence in the catchment area of the sampling site, right? So this actually requires a different kind of model. Again, you need models, mathematical models. Yeah, but it's also really interesting to do. But there's something else. Suppose you have an environment where you have sewage and the contributions come from a limited number of sources. So you have, say, a number of different households, and each is contributing different samples. Then you can put those samples in a hypercube and then ask which household provided a positive sample. But if all contribute to the same sample, then you can also use math to ask what is the prevalence of the virus within the population. So what's the smallest number of infected people, given parameters like how much virus is being shared, how quickly it moves to your sampling site, and how long it stays there. So many interesting opportunities to use maths to answer questions that are really important in terms of epidemiology. And there are people who need these answers to such questions to take decisions that affect people's lives. Now, concerning the variant, I know that during Lavanya's test, some of the South African variant popped up in the test, but she can explain to you what was the effect, if any, on the results.
Sure, thank you for that important question. So I think that the success of the Hypercube, it largely depends on the cycle threshold value of that particular sample or the viral load of the sample. So in our lab, we've been doing routine sequencing since the start of the epidemic here. And the variant, the 501Y-V2 variant started arising, or we saw evidence of that around about October last year. But we have been doing routine testing with our normal qPCR kits, which were able to detect these variants as well successfully. We've also been doing a lot of verifications with lots of other kits from different manufacturers and different suppliers, just to ensure that we are not missing this variant. And it appears that it's still able to be well detected by our current diagnostic technologies.
That's great. Thanks so much.
Great. And just to comment on sort of first principles, so how do we detect variants? If you're using any of these testing kits, it depends on how well the primers found in your kit bind to the variant, right? So if the primer targets an area that has changed, then you might see an effect. If it targets an area that hasn't changed, then there's not going to be any effect. And so you can actually do a theoretical analysis to anticipate when you expect to find changes in the results. You get changes in the CT, the cycle thresholds.
Nice. Yeah, I'll follow up. Let others have a chance to ask.
Yeah, so we probably have time for one more question. So I see Srini has his hand up. So go ahead, Srini.
Sure. Thanks for this excellent talk. I mean, it's very rare to see something like you have a very clean mathematical model and then it translates and then you actually see its application all in one paper. So I'm looking forward to reading that paper. So this might be a slightly open-ended question, but if right now you assume that the samples are, I mean, you don't have any additional side information about the individuals from whom the samples are collected, right? So you treat them as completely independent. But there's been a lot of literature and understanding, like this comes from the computer science community, of rumor source detection, trying to do group testing kind of approaches, but to detect, say, patient zero equivalent. When there is a population where there are very few cases and you want to isolate that particular smaller cluster from the bigger network. So the question that I had was, if you were doing this, say, in a college setting or somewhere where you have a better idea of the social network, can you arrange the samples in such a way that, in addition to identifying these individuals, like because disease also spreads along these networks, so you expect them to be correlated in some sense, and so your goal may not be actually detecting one person or every single person, but just like drawing that ring around the cluster where the outbreak has started. And I think there might be a lot of applications to this when you have these variants emerging in a college campus and you want to just decide, okay, these 10 people have gotten these variants, so you might be isolating them even when there is a pandemic going on. So I think I would like to hear both from a practical point and from a mathematical point how you'll tackle that.
Yeah, that's a very interesting question. And we've been thinking about that. Not so much because we also have some other issues to address to support our experimental colleagues. So, but from a theoretical point of view, we've been looking at that. So if you look at the original Dorfman approach, it's very easy to see how correlations would improve the efficiency, right? Because if you start by grouping individuals, taking into account these social networks, so that you put people who've been interacting more with each other within the same group, then after the first round, you eliminate more of the negative individuals, the uninfected individuals, than if you are randomly assigned them to groups. So basically in the second round, you have fewer tests to do just by taking into account these correlations. Now, there are some ways, but we haven't yet worked out the math, to put related individuals in a hypercube such that it makes the detection of the positive individuals after the first round of tests very likely, right? And so, but this is really an interesting, but still open question. What is the optimal way to do this? I suspect that the solution might also take into account that the fact that within a hypercube, we have a structure that can represent to some degree these relationships between people, right? So already taking that into account when putting these individuals in a hypercube, in contrast to putting people on a line in the Dorfman's approach, it's really one-dimensional. So there are likely to be some advantages, and it's something that is very much of interest to us to address theoretically and to provide solutions to our experimental colleagues who are thinking about this. So we started thinking about this when our collaborator was asked he had to investigate an outbreak in a college dorm. Okay. So
Yeah,
these are,
especially a lot of these group testing approaches, they came from detecting faulty parts and like communication
Yes,
networks and so on, where they're all independent. But then once you start bringing in this network aspect of it, where these will happen in a cascade kind of fashion, you would like to leverage it to minimize the number of tests.
yeah. Exciting, and we're still thinking about the best way to do it.
Yeah. Thanks a lot. Yeah.
Yeah, I think we're out of time for today, but I'd just like to thank our speakers, Wilfred and Lavanya, again, and thanks to everybody for joining us.
Thank you very much. It's a super talk. I hope we can work with you folks in the future, and very soon, Wilfred is on our steering committee as well. But hope to keep in touch and start some collaboration as we had discussed many times.
Yeah, thanks a lot. I think there are lots of opportunities to do a lot of good. And thanks for inviting us. Thanks, Lavanya.
Thank you. Thank you for the great opportunity. Lovely to meet you all.
Yeah, take care. Thank you very much.
And
folks.
you. Thank you.
Everyone.